All right, so you guys can read in the book to see where this double sum comes from. My goal in this video isn't to show you where that sum comes from, but my goal is to explain how they get to that final answer from this double sum. All right, so just in case that wasn't clear to you, hopefully this will clear things up a little bit. So when you're doing a double sum, the way we can handle this is let's just focus on this first sum by itself. All right, so to focus on this first sum, the thing I need you to realize here is that our index starts at j plus 1 and goes to n. Our index is I. Notice our index I does not show up anywhere in this expression 2n plus 3. So we're basically, as far as our index I is concerned, we're adding up a constant. All right, so this is why over on the right hand side I just kind of showed you some basic examples. If I'm adding up from I equals 1 to 5 to number 3, then my sum, starting with I equals 1, I've got 3. I equals 2, I've got 3 again. We've just got this constant 3 showing up every time. It does not depend on I at all. So I end up adding up 3 5 times. All right, now we can generalize this a little bit more. Here, again, this, instead of being a 3, this is 2n plus 3, but again, as far as our index I is concerned, this is just a constant. So same thing here, if I'm going to add this up n times, I would be doing 2n plus 3 plus 2n plus 3 plus 2n plus 3 n times. So I would end up with 2n plus 3 times n. Now on this last sum, we're still adding up 2n plus 3. Our index is still I. 2n plus 3 does not depend on I at all, so this is still considered a constant as far as the series, or as far as the index is concerned. So this is still going to be 2n plus 3 times however many of these 2n plus 3's we have to add up. And if you think about this for a minute, you'll realize that you're adding up n minus j of them. I guess I can go ahead and show you kind of the basic idea on where that n minus j comes from. Back up with this first example, we had 5 3's show up, right? How can we relate that to the numbers in our index? Well, if I just do 5 minus 1, I get 4. But then I have to add 1 back to get how many 3's showed up. Same thing here. This is kind of a silly exercise. If I do n minus 1, that almost tells me how many of them there are, but then I have to add 1 back to make sure I get all of them. And that gives me my factor here. Same thing here. If I want to know how many of these 2n plus 3's I'm adding up, it's n minus j plus 1. And then I have to add 1 back to make sure I count them all. So this is n minus j minus 1 plus 1, which is n minus j. Okay, so that kind of explains this first sum. This first sum gives me 2n plus 3 times n minus j. All right, so I've got, now I need to do the sum from j equals 1 to n minus 1 of 2n plus 3 times n minus j. All right, so now how do we handle this sum? So first of all, you'll notice in the book, again, since our index is j and this factor does not depend on j at all, we can bring that outside the sum. Now the next thing I want to explain to you is where they get this, where this k comes from. All right, so you'll notice in the book, this sum here, they rewrite it as the sum from k equals 1 to n minus 1 of k. All right, so they take this sum and rewrite it this way. All right, so where in the world does this k come from? If that threw you off or you're not convinced that we can write the sum this way legitimately, let me just give you a brief explanation on the next slide. Now what I have here at the top is just a repeat of what we had on the previous slide. So where we left off is we had this sum where this sum from j equals 1 to n minus 1 of n minus j. In the book, they just rewrote it this way: sum from k equals 1 to n minus 1 of k. And I know when you're reading these things on your own and you're not used to reading this type of stuff yet, when you see these sudden changes without explanation being given, it can catch you off guard and you can be confused and be wondering where in the world this k came from. But I just wanted to show you quickly how to handle this kind of thing. So when you're reading on your own, when you're reading math and you guys are learning for the first time maybe how to actually sit down and read math going through this book, sometimes you have to just kind of take a step back and slow down and think through things a little bit more carefully and process them. You can't read this stuff like you would read a regular book where you just keep moving along. You really need to stop and make sure you understand where each line is coming from. A typical practice in math when you're first trying to understand something is to break it down into a simpler example. All right, so we talked about this with the Gaussian elimination code in the previous video, the idea of just starting with a simple version, and then that helps you understand where the general concept comes from. Hopefully, as you start to read through and get used to reading on your own, you'll develop this skill where you'll kind of pick it up and do this kind of thing automatically, where you'll see something like this and think, okay, I don't know where this is coming from, but let me just look at a little side example to see if I can make sense out of it. So that's what we're going to do down here. So again, let's start with this main sum we were focusing on, the sum from j equals 1 to n minus 1 of n minus j. And here, just for the sake of doing a simple example, I just chose n equals 6. Remember, n represents the size of our matrix. So here, in this case, I'm saying that we're dealing with a 6 by 6 matrix, all right, just to give me a concrete example that I can grasp. So I'm dealing with a 6 by 6 matrix, and the whole idea here is to figure out how many operations are needed to do Gaussian elimination on a 6 by 6 matrix. All right, so if I'm doing the sum from j equals 1 to n minus 1, well, n minus 1, if n is 6, n minus 1 obviously is 5. So I'm doing the sum from j equals 1 to 5 of n minus j. Or sorry, we know what n is. N is 6. 6 minus j. All right, so if I break this down, do each term in the series, this is 6 minus 1 plus 6 minus 2 plus 6 minus 3 plus 6 minus 4 plus 6 minus 5. Right? I start with j equals 1, and I end when I get to j equals 5. But if I think about each of these terms, then this is obviously 5 plus 4 plus 3 plus 2 plus 1, which is really no different from writing, obviously, 1 plus 2 plus 3 plus 4 plus 5, which is exactly the sum we have here, right? We're starting at 1 and stopping at 5, right? N minus 1. And we're just adding whatever my index number is. So here, this is no different from saying the sum from k equals 1 to 5 of k. And again, k, in this case, 5 is our n minus 1. So now if I want to generalize this, if I want to do this for any n, then for any n, I get exactly what we had up here. The sum from 1 to n minus 1 of k. Alright, so that explains where this sum comes from. And then the last thing I want to mention, something that they use in a couple of the computations in this section are some formulas that you've probably seen in previous classes, but I just want to mention them briefly. So this sum from k equals 1 to n of k, or no, I guess in the book they use the index m. The sum from 1 to m of k, there's a shortcut formula for this. It's m times m plus 1 over 2. Alright, you've probably seen that in maybe like a Cal 2 class, or even earlier than that. You could have seen it in a pre-cal class or an algebra class even. But even if you've somehow never seen this formula, or you've seen it and completely forgotten about it, it's pretty easy to verify that this works. So I'm not going to give a proof here, but just a quick example. Really, the proof isn't that difficult, but let me just give you a concrete example. If I want to do the sum from 1 to 4 of k, that's 1 plus 2 plus 3 plus 4, which gives me 10. If I want to use my shortcut formula, in this case m is 4, so according to my shortcut formula, this would be 4 times 4 plus 1 over 2. That's 4 times 5 over 2, which again gives me 10. Alright, and if you're interested, this would be a good little exercise to either see if you can prove this formula on your own, or at the very least look up a proof of this formula. Again, it's fairly easy to follow if you do look it up. And they also use this formula for not just k, but k squared. If you want to do the sum from k equals 1 to m of k squared, the shortcut formula there is m times m plus 1 times 2m plus 1 over 6. That's another little shortcut formula that they're going to make use of in this section as you read. And in fact, I'll just write it right up here. At the very end of this section, they even generalize this more. They say that if you're doing the sum from k equals 1 to m of k to the pth power, this is equal to m to the p plus 1 over p plus 1 plus order p, or we've got order m to the p. So in other words, if you're adding this up, then you're going to get something on the order of m to the p plus 1. We saw that here. If I'm adding up k squared, all right, so back down to this sum, in this case p equals 2, and notice here I've got m times m times m. I'm going to have an m cubed showing up. All right, so this is this sum is on order of m cubed, and then there's lower order terms that are added as well. All right, so we've got order m cubed showing up in this sum. And this other one, in this case, p equals, so this one here, p equals 1 in this case. And again, we've got an m times an m. So this is on order of m squared, p plus 1. So we've got m to the p plus 1 is how this sum is behaving. All right, so these little sum formulas can prove pretty useful to us. The only ones that in this section, they don't necessarily use the general one. They talk about it at the end of the section. The main ones that they're going to make use of are these two specific ones that we talked about just a second ago. All right, so hopefully that all of that will clear up some of the questions you may have had while reading this section. If there's anything else in this section that's giving you a difficult time, please reach out to me and I can either make a video explaining it to you, or we can do some office hours with a video call. Whatever you need, we can get those questions cleared up. All right, so let me know if there's anything I can help you with.